All right, so as many of you know, we had for the spring build-a-thon, we had one of our offers was a kit that a fellow in France had, well, kind of put together. It really wasn't in kit form, but it sort of kind of was if you got all the parts and put them in a bag or a box. But one of the things that several of you asked about was, well, what can I use this vector network analyzer thing for? What kind of work or what kind of problems is it good for? So I'm going to try to answer that. It is, there's a short answer and a long answer. And I'm going to give you the short answer, the short general answer, and then I'm going to give you an example that's essentially the rest of the presentation. Okay, that's the long answer. Can all of you see this okay in the back? I hope. Okay. Yeah, no, it's going to be a challenge. A scalar network analyzer, which is the first type, is essentially a signal source and a way to measure a loop back from that signal source, essentially through a device under test of some kind. So a good example of a scalar network analyzer in a simple form would be an antenna analyzer. So something like your MFJ 259s, other brands of course included, that give you VSWR information and potentially other pieces of information, are working with a single port, which we'll get into in a second, and they're looking at reflection. So they're going to do transmission out and reflection back. They use a directional coupler to see the power reflected back, and then you can arrive at voltage standing wave ratio, among other things. It's also the same in effect if you have a spectrum analyzer and it has a tracking generator that allows you to set a stop frequency range, then you can use that to test filters or other devices. You can actually tune your antenna with it. There's a number of things you can do as long as you have a directional coupler or a bidirectional coupler. Directional coupler is the most common kind. That gives you reflected only. So forward power, if you will, is usually assumed to be a function of how much output the tracking generator is set to. So if it's 0 dBm or plus 10 dBm, and that's what you're driving the circuit under test with, you know that already, and so you just need the reflected back to get some information. A vector network analyzer, on the other hand, goes a little bit further because it adds phase into the picture. So not only are you making magnitude response measurements the way you would to trace out the characteristic of a low-pass filter, for example, but you're also measuring phase at every point that you sample. So what that opens up is orders of magnitude more in terms of feature and functionality and usefulness, having the phase information than simply just having the magnitude information. And in the next slide, we'll look at some of the ways you can make use of that. So the signal source is applied by the analyzer itself, much like the spectrum analyzer's tracking generator. That signal source comes from the VNA. Most of you have probably heard of a level sine wave generator, and the idea there is that you get a constant amplitude across a broad range of frequencies, usually within 1/10 of a dB or less. So a very flat response output to drive a device under test. Why? Well, you kind of need a baseline like that if you're really truly going to measure the response back, whether it be reflected power or impedance or admittance or what have you. You really need to have a good solid signal source as your basis. The other reason for that is you want something that's stable, of course, because if, for example, there's one frequency of interest, which you'll see here in the presentation, you don't really want to guess as to where the accuracy from a frequency standpoint is, right? If you were tuning an antenna and you were interested in a center of the band frequency, then you want to know that when you get the information back that it's accurate from start to finish and center, right? So those are really the two reasons that they build the single sources in, and of course it's a convenience too. You really have a kit that has everything built into it, has the output, has the input, and the rest of it is all menus and buttons for device settings. Now, as I mentioned, the amplitude and the phase response is a series of samples. So you have a phase detector as well as a magnitude detector. What really makes it special is the phase detector, because as it turns out, long story short, that's not the easiest thing to build in a way that's linear across the set of frequencies. They're not hard to build if you're just interested in a very narrow range of frequencies. You can get phase, but across the broad spectrum of frequencies, that's a little harder. For something like this kit, the analog devices chip in there that does the phase detecting, which was the most expensive part of the kit, I think it was $42. That's a very specialized chip, but that only covers a range of about 1 to 60 megahertz, okay? If you were to look at an Agilent or an older HP vector network analyzer that often is in 5 digits cost, sometimes a little bit less if it's broken, you're talking about some very specialized piece of equipment, highly tuned, highly exacting specialized equipment. So one of the reasons that you don't get a lot of hands-on time, like an oscilloscope as a ham, is because of the cost, let alone a spectrum analyzer. Spectrum analyzers used to be that high, they've come down, and now you have some handheld vector network analyzers, some of which can go to 4, 5, 6 gigahertz, that are pretty affordable, right? They're not giving them away, but if you're looking to spend the kind of money that you would spend on a scope to get a good grade VNA, you can get them for about $500, $600. So, not too bad. So, as I mentioned earlier, a one-port network is the idea of driving a current into a network, a set of devices, right, an electrical network, with a return path. So it could be a differential input, but it more often than not in our world, it's a coaxial or single-ended input. So you're going to have a current that goes in and a current that comes out, and because it's AC and because there's a frequency component, you can start to make some measurements that kind of give you some information about, for example, what is the characteristic input impedance for that single point, that single port. Two-port network analysis, which is really where vector network analyzers excel, really looks at both the input and the output. And when you get to S parameters and other parameters, which we'll talk about soon, then what you really have to do is you have to say, if I'm trying to match, let's say, a mixer circuit or an IF amplifier, then I know I've got an input and an output. How do I characterize the input impedance and the output impedance? I know if I have a common emitter or a common base, right, or a common collector circuit, that I know about where the impedance is going to be in terms of both DC and maybe low frequency. But what about at higher frequencies? How does my board affect my circuit, right? And we're not talking about perf boards with wires hanging out of them, right? Because that's meaningless in this realm. You're talking about well-designed RF circuits. So either something in the HF range that isn't so fussy, like this device works with, or in the microwave range today, working with 4G or 5G, you're talking about 6-figure test equipment, right? For 5G, they're looking at 24 gigahertz. So all of these measurements have to be doable at 24 gigahertz. And if you think about that for a second, that's pretty challenging, right? And Keysight, for example, or Anritsu, or Roden Schwartz, they're going to want $100,000 plus for that piece of test equipment, and most people will lease it, and it will eventually get in the used marketplace and get leased and whatnot. A few companies are not going to spend that kind of money up front, but an AT&T, a Verizon, they might. Right? A Samsung, they might have to, so the device manufacturers. Motorola used to do that. And in a lot of the auctions that have been in the last couple of years, as Motorola closed cell phone plants down, you could get a lot of this equipment at a fairly good price. Half of it went into the used market lease rental space, but the older stuff with the HP labels and some Agilent equipment came in through the auction sites. So I mentioned what a common one-port measurement is. The two-port measurements, as I said, are more interesting because you can cover a useful, interesting device under test. It can be an amplifier circuit, it could be a passive circuit, it could be a complex network, it could have balance, it could be an RF amplifier for HF. That you have to understand the impedance match between the stages, even if it's one stage coming in and coming out of that amplifier. So there's a lot of uses for it. You can measure the Z parameters, which give you impedance, the Y parameters, the admittance, that give you small signal gain information in a vector matrix. The H parameters, similarly for amp circuits, that give you current gain related information. And then for us, the most interesting part are the wave transmission reflection coefficients, the so-called S parameters, S standing for scattering parameters. I don't know if the last statement really is necessary. Most of us are extras in the club, but you all know that in a polar coordinate system, you're going to have a vector is going to be a magnitude and a phase, right? So that essentially makes up your vector, and why VNAs are called vector network analyzers. Just my eyes getting fuzzy. So here's kind of a block diagram layout of what we're talking about. You have a variable sweeping continuous wave, leveled sine wave source, the level adjustment with a feedback mechanism that's not shown here, a switch capable of switching with as near zero loss as possible at the frequencies of interest, a couple of splitters, and as you may know, as you go up in frequency, the simple notion of a splitter starts to get pretty difficult as you go up into microwave frequencies. Then we have our couplers, two of those. The precision cable, which is PC1 and 2 here, is really only something that comes into with cables like that are manufactured by Megaphase. I was saying at the break, can cost, just the shortest ones I know of are about a foot, but they're metric in length, and they run about $150 a piece new. The reason for that is when you get up into the gigahertz range, you can't assume what's going on with phase in that cable. So as you send the source signal, things could be happening to it at multiple gigahertz, let's say 18 gigahertz, that you might assume wouldn't happen, but in fact are. And so when you go to make a measurement back coming around on the loop, your point of reference could have shifted. So in HF frequencies, you don't have to worry about any of that, which is nice. So the VNAs, like this kit and like the commercially available ones, I see MFJ has one now that they came out with this year, they're able to get away with a lot at HF frequencies, and so you don't need a lot of special cabling. You don't have to you do have to calibrate a VNA, you always do, so you need to make sure that that CW source, which is typically a DDS, is on frequency as close as possible, okay? And you have to make sure that the reference oscillator as well is in sync with that. Now, typically these can be the same circuitry, but one that'll sweep and one it'll tick back and forth. The other thing they do is, because, and this is the case with this kit, is that the DDS actually has 2 ports and 2 programming modes, so it can run simultaneous frequencies. So you can take a point of interest for the reference oscillator feeding into the receivers, or what they're calling receivers in this diagram, and then make a comparison from the leveled sine wave here to the device under test in terms of what's been reflected back. And then of course this just simply means you've got a processor, in this case an Arduino, that's crunching some numbers based on some voltage information that's coming back in and being digitized. When you make the measurements in port 2, all that really happens is this switch comes over and you do the same thing. So you could do both transmission and reflection measurements on either port. You can see input impedance, output impedance. You can see the scattering parameters, because there are 4 of those, and in a 4-port or 4-wire 2-port network, you have 4 scattering parameters. So you have S12 and S22, if I recall, and then S21 and S11 on the output, something along those lines. I never tried to memorize them, because I'm always, if I care about it, I'm using a piece of equipment that just tells me what they are anyway. So this is the kit sitting on my bench that I had put. I brought this in last year, I think, end of last year, and it's just sitting in some PCB more for a case than shielding or anything, because again, at HF frequencies you don't really have to worry about that. That was about $100 cost type of undertaking, which is pretty good, because the commercial ones, some of the cheaper ones like the MFJ now, are still up in the, I think, 300 and above range. So it was still pretty good value for the money. Okay, well, when can a VNA be a handy thing? Well, lots of situations that I've already mentioned, but let me back up and tell you about a situation I had. So earlier I was asked, well, by Craig, what am I using for a 30-meter antenna? So long story short, I decided to build another off-center fed dipole. I had a 15-meter dipole up there. With the conditions the way they've been lately, since we're still near a solar minimum, 15 meters has been a little bit dead. So I said, well, you know, it's been up there 3 years. It's starting to get aged a little bit. I'll take it down, take the balun I built for it out of there, and, you know, put up a new antenna. So I knew between the poles on either side of my house, I had close to 50 feet to work with. And I had been running Whisper on 40 meters on the commercially made antenna that I purchased. So I wanted to get Whisper off of that, because I wanted to put my rig back on the air and not have to switch back and forth with the rig switch. I'm one of those people that learned, because I was a service tech, not to have switches on your transceivers, because sure enough, you'll have it in the wrong position, key down, and blow up the other transceiver. So rather than try to keep that straight, I've always just stayed away from it completely and always switched the antennas only. And if I have to physically move coax, I physically move the coax. But so I wanted to get my ICOM going again back on the air, since the Whisper transmitter was using the other dipole. So I said, well, all right, 30 meters works. I haven't really done much on 30 meters. I can't really load 30 meters very easily on the other one, because it's set up, as you'll see from the plots, the way a typical OCF 40 would be. It does 40 meters, 20 meters, 10 meters, and 6 meters. Those are all the resonant points. Those are all the dips in the SWR, and they're multi-band. So the guy I bought it off of out in Pennsylvania, I contacted via email, real source of knowledge, fountain of knowledge on off-center fed or Wyndham antennas. And I said, building a 30-meter one, what do I got to watch out for? And he said, well, you can't do 15 meters on it. I said, I don't want to do 15 meters on it. I don't care about any of the harmonics, right? Which confused him a little bit, because he was like, well, why would you build an OCF if you don't care, if you don't need it to be multi-band? And I basically said, because I can, right? I mean, because I want to. I just want to try it. So I want to wind the ballon again. I want to, you know, it's a project. So I don't need a reason. That's the reason. The 15-meter deal was a straight dipole, and I got lucky because we're talking about a center of this structure about 22 feet. So I'm low to the ground. And as it turns out, in this learning experience, I found out that 40 meters is very different at that height than 30 meters is. Now, you wouldn't think there'd be that much difference, but there's a tremendous difference. The feed point impedance at 30 meters on an off-center fed antenna at 22 feet is much lower than a book will tell you. A book will say it should be around 200 ohms. And you'll see cut it at the 25, 75% point, or cut it at the 1/3, 2/3 point, and insert your feed there. On an off-center fed antenna, this is just general information in case some of you don't know this, the current maximum in the middle is still at the middle of the wire, just as if you were feeding it center fed. Okay, so nothing really changes that way, except the impedance, the feed impedance changes. So, dumb me, I figured, well, I'll put a 4-to-1 ballon in there to go from 200 to 50 ohms, until I found out through John Krause's book. Now, that's an academic book. That's a book that you're going to, if you're studying electrical engineering, and probably in the 50s and 60s and maybe 70s, you would have had in a specialized grad student class, because you would have studied field theory in your undergrad, and then you would maybe take a course in antennas. Now, Craig laughed because he knows the name, and a lot of you guys know the name.
Yeah.
John Krause is the guy, and has been for decades, on antenna theory. He did a lot with NASA to be able to pick up the telemetry from the moon, from the LEM and all of that. So he knows his stuff, and he had in there a chart that showed feed impedance versus distance off the ground in fractions of a wavelength. So in there, I figured it out just real quick, right? What fraction of a wavelength at 22 feet I was at. And sure enough, 100 ohms. Okay, so I'm giving you kind of the punchline here. So my 4-to-1 ballon was turning my impedance as seen. There's the 40-meter OCF and all the points from 40 to 50 megahertz, or 7 to 50 megahertz. And there's where I started at about 1.8 to 1. Direct, no tuner, and that was an objective I had, is not to use a tuner. I wanted to get to a very close feed impedance that was accessible. And 1.8, 1.9 to 1, I'm already using 0.2 of a watt. I don't really want to lose anything more at 0.2 of a watt, because it's going to be logged as 0.2 of a watt, even though it effectively is less than that. Should get the best out of it that I can get. Well, it turned out that the whole reason for this is because I was seeing 25 ohms at the coax on the transmitter. Times 4 is 100. Right? Well, the VNA helped me with that to understand what kind of parameters I was dealing with. But any analyzer, any good antenna analyzer would do the same thing. However, interestingly enough, the MFG 259C that I've been relying on for several years didn't tell me this at all. This thing did. It was spot on the impedance, whereas the MFJ unit was way off. And I was like, wow, that's, I mean, you know, mighty fine junk and all that, but wow, how far off is this? From a standing wave ratio standpoint, it wasn't off. It was actual vectorization of the impedance that wasn't even close. So I don't know if that's a bug in their firmware or what, but anyway, when I plotted this out, and it's an eye test already as it stands, but I'm going from a best case VSWR of, in this case, 2.6, so I was cutting the antenna and whatnot, and then with a tuner, or sorry, at 9.4 megahertz, I was down at 1.4, and at about 63 with 12.2 on reactive, which is all inductive on the top of the Smith chart, all capacitive down here. And for wire antennas, you can expect them to traverse the Smith chart up in the upper half because they're going to tend to be inductive. So because the whisper frequency for 30 meters is in one place and only one place, really the only frequency of interest you care about is 10.140. It's actually 10.138, blah, 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 on upper sideband, but it's about 10.140 megahertz. And as it turned out then, after I corrected the problem, an interesting thing happened that I know can happen. I didn't expect it. I don't know that you could predict this. I didn't see anything that would lead me to believe that you could predict this. But as a 5/8 wave antenna, it's resonant at 14.2 megahertz. Now that's kind of unusual, it's kind of unexpected. You won't find in any of the books that say an off-center fed antenna will have 5/8 wave or 1.5 wavelength points or anything like that. Books are books, they cover the general stuff more than the real world, they cover the theory. But interestingly enough, that came out to about a well, this is 1.1 to 1, and this one I think was about 1.15 to 1. Now, it is so close to the 20 meter whisper frequency, I got really lucky. I can switch the unit that I use, same one that you have, Steve, that is made by Hans Sommer, and I can put it on 40 meter or 20 meters instead of 30 meters, and I don't have anything to do. So that was just dumb luck there. But I wouldn't have known I could do that without a tuner unless I had some way to plot this and measure it. I mean, I just wouldn't have known at the SWR unless I just happened to, you know, stumble into it. I wouldn't have known that the SWR was up because this is on a wide scale, but believe me, those spikes are very narrow. Very high Q, very narrow bandwidth. So it's a difficult thing in a way to kind of get your arms around. This one is just an 8 to 12 megahertz approximately scan, and the traversal starts off here, goes down to my 0.2, which is 1.1, hits the second best at 1.3, which is a frequency of 10 to 205. That's kind of a weird one there. And if I went out to 14, it would loop around there and hit the 14 megahertz point as well. I think that's it. Yeah. So, in summary, my little $100 kit turned out to be very useful. I knew that it could do some things. I have other equipment that I could use, but in the case of the antenna analyzer, I'm about ready to take it to the shooting range because it's pretty much useless for anything other than just raw VSWR. That's not a surprise. I mean, I've been told, I didn't know any better, 5 years ago or so when I got licensed, that MFJ was mighty fine junk. I think some of the products they make are okay, but if you're asking for precision, even in the HF band, you might want to look at somewhere else, right? So really, it helped solve the problem that I had, and I thought it was kind of an interesting outcome. So, any questions?
Yeah. Why do you like the Offcenter Fed?
Why did I go with the Offcenter?
Why do you like it? Yes.
Well, there's a couple different opinions out there. I mean, I'm sort of bottom line-ish about things. That antenna has been rock solid. The one I bought has been rock solid for as long as I've owned it. The guy did an excellent job with everything. The wire that I bought for the 15 meter in 3 years, the insulation cracked and was starting to peel off, and it was your standard THHN wire. The wire on the dipole, perfect. Everything's perfect. The connectors, the insulators, everything like the day I put it up. It's high quality stuff. It will take 5 kilowatts, don't care, but it's heavy. It's got heavy duty current balance in it. 2-core balun instead of single-core balun. Some of the theories on Wyndham and why people like them, as you may know, it started out being a wire-fed, a random wire-fed antenna, and people have thought, have looked at it in terms of launching, which is a term you typically associate with traveling wave antennas, but essentially kind of a crack-the-whip effect because it has a very high voltage and impedance on one end and a reasonable impedance on the other end. So I maintain, I've been part, I'm no longer, I've been part of antenna discussion groups with physicists and other folks. I maintain nobody really truly yet understands everything there is to know about antennas. I think we have some good practical guidance on them. But when I see people like in QEX that try things with antennas and they come up with something really goofy, novel, and it works well, you can't argue with their success, their results.